started, you think, Sophia?
Yes.
Lily says it has started. Which ones do we need to do? I know about 62 and I know about 76. Any others? 71. Any others? We may not have time to do all 7, so choose wisely. Yeah.
How about 83? That was pretty. Oh wait, no, 77.
77.
Because I didn't go to gym.
Okay, that's 4. Do you want to do one more or those 4?
It's just
83.
Unless somebody else wants to do it.
All right, let's go back to 62. And today is Friday, September the what? 28th. Everybody who went on the Spanish trip is enjoying tacos right now, which is more important than AP Physics, I understand. And there's some other people out for other reasons too. That's okay. All right. That's a little bit of sarcasm. I shouldn't have said that. I should start over. Should I restart the video and leave out the sarcasm about the tacos?
No, you should leave.
You should have leave it.
Okay. Who's gonna read? 62. Who's gonna read? Out loud. Volunteer.
I'll get it.
All right, Kyle, go.
A mountain climber in the process of crossing between 2 cliffs by a rope pauses to rest. She weighs 535 meters. As the drawing shows, she is closer to the left cliff than to the right cliff.
Oh, wait, there's a drawing. I should look at the drawing. Oh, okay. And that says 65 degrees and that says 80 degrees. But let me draw. Picture. There's a rope. There's a mountain climber here. And she's hanging on for dear life. And then there's a longer rope here to this other cliff. And what you were told, I think, was, no, you were told this was 65 degrees, is that correct? And this up here is 80 degrees. And so here she is, and not in the middle, closer to the one on the left. All right, go ahead. What else? And that's her weight. All right, go ahead.
Find the tensions in the rope to the left and to the right of the mountain climber.
All right, so let's just call this T tension 1. I'll put F sub T for tension. That's number 1 on the left. This is tension number 2 over here on the right, just so we know they're not the same. The tension, which one, just looking at it, can you tell which one would be greater? The tension one would be greater. Okay, so if I'm going to actually draw the free body diagram, which I am, we always do that. You've got the weight of the person, which we know is 535, that's straight down, mg. You've got tension 1, which is this, and you've got tension 2, which is this. Now, notice I didn't draw tension 2 as long as I drew tension 1 because I already know tension 1 is going to be greater. It's a shorter rope, but it's more tension. Okay, so the length of the vector it tells you something about the magnitude of the tension. So I drew the tension 1 a little longer. That's the vector. Now they have components. Those are green, but the components are going to be in red. So here's my tension 1 X. Straight up is my tension 1 Y. And I was told this angle, what angle was I told? This angle up here was 65 degrees. That's the angle that they gave me, I think. All right. Over here, the components would be this one, that's tension 2X. Straight up is tension 2Y. And tension 2Y. And that angle up there is 80 degrees. Okay. Now, that's not drawn very well, I'm sorry. Oh, I know, because I didn't use my vector, I used the rope. Let me redo that. My vector was in green and it only goes to there. So this one should be more like that, where this is tension 2X and this is tension 2Y. Okay. Now, the reason that's a better drawing is right now the person's in equilibrium, which means not moving. not accelerating, right? So one thing we know is the sum of the x forces must be 0, which means these are the only two x forces. They should be the same length. If you really drew it correctly, that one to the right should be about the same length as this one. It should look that way on your diagram, because they've got to add up to 0. The person's not accelerating left and right. Then the y forces would also be 0, which means this one, it doesn't mean this one's equal to that because they're not equal. The F1, the tension 1 y is greater than the tension 2 y, but they're both up. And the point is the two ups should equal the down. And so probably if I'm really drawing it correctly, the down would be kind of this plus this, which is maybe something like that. Okay. Now, Freebody diagram, I take the time to draw it because all my math is going to be based on this drawing. You don't want to short circuit yourself by not really getting a good drawing. If you don't really have a Freebody diagram, you're kind of lost. Because I'm going to base everything on that. And the two things I have going are the sum of the x forces is 0, and over here I'll put the sum of the y forces is 0. I'm not going to get very far with the x forces. I already am disappointed with that blue one. I've got another blue one here. Not going to get very far with the x forces. It's simply that the tension 1x has to equal the tension 2x. That's this horizontal to the left has to equal that horizontal to the right. That's the sum of the x forces equals 0, and each of those, tension 1x would be tension 1, which is the green line, times the sine of, because this is my angle up here, and the x is opposite that, times the sine of 65. And tension 2y would be tension 2 times the sine of 80. That's this one, and that's the 80-degree angle over there. Okay, there I've got two, F2 and F1 are not the same. So that's two different unknowns. So I've got an equation, but it's got two unknowns. I can't go much farther than that. I could simplify that, which I'd probably like to eventually, because I'm going to end up with two equations and two unknowns. So I'm going to go ahead and solve that for T2. Tension 2 then would be equal to tension 1 times the sine of 65 divided by the sine of 80. And you can go ahead and calculate that just to get a simpler equation. All I'm doing is math right now. And I get Ft is equal to, I have F2, that's tension 2, is equal to 0.9136. Okay, so here I've got a number. No, times T1. I knew that wasn't right. Okay, tension 2 is equal to 0.9136 times tension 1. You still have an equation with two unknowns. All I did here was simplify it so I can use it later to solve. But right now I can't go any further. I've got this equation with two unknowns. So I go over here to my y forces. They add up to 0. The y forces are tension 1y, that's that one, plus this one, tension 2y. Those are both up, so they're both positive. And that has to equal the down, which is mg. And we know mg is 535. We've got a number for that. These would be tension 1 times the cosine of 65. That's this, because the y component is adjacent to my 65-degree angle, so I use cosine. And then tension 2y would be tension 2 times the cosine of 80. Because that's my y component, and it's adjacent to my 80-degree angle. So I use cosine there. So in the y direction, I have this equation with the same two unknowns, tension 1 and tension 2. Now the rest is math. You've got two equations with two unknowns. And since I've already solved that one for tension 2, for me, if I've already done that, it's simple just to take that and plug it into tension 2 and then solve the whole thing over here. So I'm gonna say tension 1 times the cosine of 65 plus, instead of tension 2, I'm gonna write that, 0.9136. This is just how I'm doing it. You can solve these things in a number of ways. Times tension 1 times the cosine of 80. See, all I did was plug in what I know for tension 2 right there. The rest is the same, and that's equal to 535. There you have an equation with just one unknown, it's tension 1, and you can solve it. And when I solved that, I got 920 newtons for tension 1. Maybe that's rounded off, I don't really remember, but that's the answer to tension 1. Once you get tension 1, it's a simple thing to go back to this, plug 920 in right here and multiply that to get tension 2. And that one I have came out to be something like 841. So tension 2 is equal to, I'm going to round it to 840 newtons. There are the two answers. Now, do you see what I did? First step is get a good free body diagram. If you're still struggling with that, that's why you're getting the answers wrong, because that's where it starts. Get a good free body diagram, then you can just look at it and see, oh, these two up forces have to equal the down force, and that's your equation right there. And this left force has to equal that right force, and that's my equation right here. So it starts with that diagram. Okay. Moving on. That was 62. That was supposed to be kind of hard just because it was long and involved. We had two equations with two unknowns, which some of you don't like. Some of you don't like that. Do you like those, Sophia?
No.
See? Some of you don't like that. Do you like those, Lily?
No.
See? Steve, do you like those two equations with two unknowns? Yeah, Steve likes them. See that? Yeah. You should all like them. It's just algebra, isn't it, Steve?
Right.
It's just algebra. It's not hard. We're not doing any calculus here, Jaden. Are we?
No.
Okay. Are you all right? Okay. I didn't know if you were, if you had zoned out on me or not. I couldn't tell. You were. That's all right. Number 71. That's what we're doing now. Who's going to read? Oh, I got it. Somebody, go ahead.
He's got Kyle.
Kyle has it. Go, Kyle.
Only two forces act on an object. Mass equals 4 kilograms, as in the drawing. Find the magnitude and direction relative to the x-axis of the acceleration of the object.
What's the drawing look like? 60 up and 40 to the right. There's the object. 60 this direction, 40 this direction. And the question was, what was the question? The net force?
Acceleration.
Acceleration, okay. What's the acceleration of the block?
Magnitude and direction.
We're going to get the acceleration by the sum of the forces equals ma, because we know m was 4. We just need to know what is the sum of the forces. And this is not a hard one. These are perpendicular, so I would still draw it head to tail, which means take one of these, like take the 40 and shift it up to here so its tail is attached to that head. When you draw it that way, you've got a 60 and a 40, and the hypotenuse is the net force. When you draw it, when you put it head to tail, you can just make a right triangle out of it and find the hypotenuse, and then it all got easy all of a sudden. So, Pythagorean Theorem, 60 squared plus 40 squared will give me f squared. And that comes out to be, I don't know what, I didn't write it down, but that's not hard, you can do that. What is it?
18.
It's a,
Yeah.
it is a 3, 4, 5 triangle. So it's 100, and therefore this is 100, and it's equal to m times a, and the a is 4, and so it looks a lot like the a is 25. Is that really true?
I don't think so.
I don't think we found
The
it.
C is 72.
Yeah.
What?
60 squared plus 40 squared equals 5,200.
So it's not 100?
No,
Nah.
Or what is F? Somebody tell me what F is.
200?
72.
72 looks more like it. It's not a 3.5 triangle. No, it's not.
Oh wait, oh, we're on the wrong one.
Okay.
That's the first question.
Okay, so it's not, it's not 25, it's 72 divided by 4, whatever that is.
18.
18. Now, if you need a direction, did it say, it probably did,
Yes, it did.
that would be the magnitude right there. But if you need a direction, you need to find, so look at the force, look back at this head to tail triangle. That's the direction it's accelerating, which over here would be that direction. So you can find, I would probably find that angle, which is the same as that one. And I would use the tangent, because I'm certain about the 40 and the 60. And so if I use the tangent of theta, that's equal to the opposite 60 over the adjacent 40, and I can get the angle that way. I don't have that written down what it is, but that would give you this angle from, if you found that, that's this angle here, which is that many degrees from the positive x-axis. The problem, I don't think, said anything about other directions, like it's not north and south, it's not, we don't know what it is. So I would just give that angle and say it's that many degrees from the positive x-axis. Okay, everybody got that? That's number 71. All right. Notice this sum of the forces was in that direction, the net force. A then is in that direction. What we've learned about vectors is that the F and the A have to be parallel. Okay, that's why we had to find the force that was in the direction of the sum of the forces. Acceleration's in that same direction. Okay, next one is 76. 76. Tony, did you get 76 right?
76?
Yeah. Did you get it right?
Just 8 parts.
You got part A right?
Yeah.
Okay, good. Did you, Cole, get 76 right? No. Well, we're gonna do it. All right, who's gonna read?
In the drawing, the weight of the block on the table is
Right.
Oh, it's one of those. These are very common. This is a great problem. Hey, you all absent people, pay close attention to this. This is a very common, you're gonna see this on your AP exam, probably, somewhere. It's always there. I go back, I'm sorry, Kyle, go back and read. Go ahead. I saw that was 422.
and the other one's 185.
185. Those I assume are the masses?
No,
They're what?
Yeah, those are the masses.
they're newtons.
There's a weight.
Oh, they're the weights.
Yeah.
Okay, so that's the actual weight. All right, go ahead.
Ignoring all frictional effects and assuming the pulley to be massless, find the acceleration of the two blocks and the tension in the cord.
All right, this is a very common setup. If there's no friction, like is the case in this problem, it's not a hard problem. You just have to kind of know how to set it up. Here's the rule that's a little different for this situation or any situation where you have a pulley. If the assumption is that once you release this thing, this one's gonna go down, making this one move to the right. And especially if there's no friction, you know that's gonna happen. Gravity's gonna pull this one down. There's no friction up here, so you know that's gonna happen and this one's gonna move to the right. All right, when that's the case, here's what I would do. The direction of motion is the positive direction. Positive direction is the direction of motion. Now that means for this block up here to the right is the positive direction, but it also means now for this hanging block, down is the positive direction. Normally we think up is positive, down is negative, but that's not the case here. The direction it's moving, we're just saying, is positive. because what we want to do is set up the sum of all the forces equals MA. Wait, what's the question? What are we trying to find here? Acceleration?
Yes, and,
The acceleration, right?
attention.
Okay, so we're trying to find the acceleration, so if you set up this equation, we made a big deal about how A and F have to be in the same direction, or parallel, and here they're not parallel. This one's accelerating down while that one's accelerating to the right, but because of this thing I just wrote up here, that in this problem is all the same direction. They're tied to a string together, so their motion is together. So we're saying that's positive, that's positive, that's positive, that's positive. Therefore, we can put all that in the same equation. It's all the positive direction. Okay, I'm still gonna draw a free body diagram though. You still start with that. Free body diagram on both masses. This one has a weight, mg, which we know is 422. And there's a normal force, which would be equal, because it's not accelerating vertically. And then there's one more force on it, which is, what's the name, how would you label this force right here?
Tension.
Tension. That's the tension in this string. And since there's no friction for the problem, there's nothing back that way. Okay, that's for the large mass on the table. For this mass, you have its weight, mg, which is 185 newtons, and you have this, which is tension. Now, are these going to be equal? No. How do you know?
It's gonna fall.
It's accelerating down. If it's accelerating down, then the mg should be greater than the tension. If they're equal, it's not accelerating, right? If the sum of the forces is 0, it's not accelerating. So we know these don't add up to 0. Okay, so I should make that make it look a little bit smaller, because it's less. All right. Now, what I'm going to do to solve the problem is set up an equation for the whole system. If you start doing one at a time, you can still do it, but it gets really complicated. So let's set up the sum of the forces for everything in the picture that's in the direction of motion. That's everything that's in the positive direction, or negative, but it's like taking my x-axis and bending it right here. Okay, here's my x-axis, and that's still my x-axis, because all that's the direction of motion. If you think of it that way, it won't be hard. So what are all those forces that are in the direction of motion? Well, not these two, and they're not causing any acceleration. So leave out the normal force and the 422, just leave those out. But there is a tension force here to the right that is in the direction it's moving, so that's positive. We said that up here. Down here, and that's the only force on that block that's in the direction that it's moving. So that's all there is. There's tension in the string, no friction. This block also has tension, but it's up. Would that be plus tension?
No.
No, it would be, that tension would be negative. Why?
Because it's going in the opposite direction.
Right, the block's moving down, and we said the direction of motion is positive. Tension is, this tension I've drawn right here is opposite that, so this tension is negative. What do you think that's going to be equal to? Tension minus tension is 0. These tensions are the same. How do I know they're the same? It's the same string. This is important. Even though they're in opposite directions, but if it's all the same string, you can't really have part of the string having a tension that's different from the other part of the string. Not unless there's something going on here at the pulley, which is one of the reasons they told you the pulley is massless. It doesn't make a difference, but there are other reasons for that we'll learn later. The point now is, you need to remember, if it's all one string, the tensions are the same everywhere, and if they're in opposite directions, they cancel each other out. So that goes away. The only other force I need to write down is what? The mg for that block, which is 185, we know, and because that's in the direction of motion, that's positive, and all that has to add up to
180.
MA. Now, what's the M?
422.
Do we know the M? Is it 422 plus 185?
It's 422 plus 185 divided by 9.8.
Divided by 9.8. Remember, the weight's equal to mg, and we're looking for M right now. So take the total weight, which is 42 plus 185, divided by 9.8, and you get the total mass of the whole system. Both masses combined here, because these forces included all the forces on both masses, so the M has to be both masses combined. What does that come out to be?
61.94.
61?
Yes.
Okay, so the M right here is 61. Now, let me rewrite this equation. These canceled out because they're the same. So what I've got is 185 newtons is equal to 61 point what?
9.
0.9 times A. And there's how you get the acceleration right there. Just divide. Okay, everybody see that? This is number 76. So I have, this is the one I got to be 2.99 when I kept 3 digits in the answer. That's equal to the acceleration of the block. Okay? Now that's the first question in number 76. What's the acceleration of the block? That's part A. Part B, I'm going to do over here so that I won't be out of range of the camera for our Mexican food eating friends. The question now is, what is the tension in the rope? Is that the question?
Yeah,
Did you say something, Sophia?
I just said oi because
Boy,
I'm already feeling like this is gonna be troublesome for me.
oh, it's not going to be trouble. I thought you were saying, oh, I'm thinking about the Mexican restaurant.
No.
Okay. Like soy sauce?
There's no.
Is soy sauce that's not a Mexican thing. I'm sorry, I take that back. That's Asian or. Do y'all have soy sauce in Korea?
Yep.
Yeah, it's good, isn't it? Pretty salty. Good though. Why are we talking about that? The tension is not hard at all. What you do is just take one block. Over here, we took the whole system into one equation. We put every force that's along this line of motion and put it in the sum of the forces. Now I'm just going to take one block, not both. Which one do you want to take? We take either one.
185.
Take the 185. All right, the sum of all the forces is equal to MA. But now I'm just taking one block, so now it's the sum of the forces just on the one block. And that would be, down is 185, which we have said is positive because it's the direction of motion, minus tension. Now those are the two forces on that one block. We're ignoring the rest of the problem just for this part. Because the question is tension, and over here tension's canceled out, we can't get it over here. So take one block and the tension won't cancel out. That's equal to MA. Now the M, though, is just the mass of that one block. The mass of the 185 Newton weight. And that mass was, I don't know what it was. This is part B. I took the other one. So it's whatever 180, it's whatever 185 divided by 9.8 is.
18.8.
18.9.
18 point what?
18.9.
18.9 is the mass of the smaller one hanging. And so the tension, 185 minus the tension would be equal to that. Oh, and the A we now know is 2.99. There you go. That's our answer over there. So now you can solve that for tension. And that's what, I don't know the answer to that. If you had taken the other block, I'm just showing you could have done either one. If you had taken that block, then the only force that matters is the one where it's accelerating, so tension's the only force you got. These two is not accelerating that way, ignore them. So if I take that block, what I have is the sum of those forces equals MA, but those forces, the sum of those forces is nothing but tension. There's nothing else that's horizontal up there. And then this mass would be the 422 divided by 9.8, and the A is still 2.99. So that's how you could have done it that way. These should be the same thing, these two answers. So you could choose either block, just center on that one block and go back to the sum of the forces on that block equals MA. Now that we know A, we know acceleration now, you can do it. All right, I don't know what that comes out to be. What is the tension?
128.6.
128 point something? Okay. All right, everybody see what we did? I was gonna try to start going fast through these, but this is a very common type of problem. It's probably every AP Physics 1 exam ever given has somewhere on the exam has had this. There's a pulley, there's something on the table, there's another mass hanging. Sometimes they include friction. And all that does is gives you another vector back this way to think about. So you would have friction over here as well. You'd have negative friction because that's the opposite way from the direction it's moving. But you would put that in. Okay, any questions about this one, 76? We're moving on to 77. 77. Do you all think anybody who's absent today is really gonna watch this video?
Yeah.
Yes. Yes?
Yes.
Do you think Claire will?
Yeah.
Claire, are you
Yeah.
watching? Do you think Lucy will?
Yeah.
Do you think Sarah will? Did you say no? Sorry, that wasn't me, Sarah. If you're watching. Moving on. 77, who's reading?
A student is skateboarding down a ramp that is 6 meters long and inclined at 18 degrees with respect to the horizontal.
Hey, time out. I'm gonna draw the inclined plane this way instead of the last 2 days I've been drawing them like this. Can I draw it like that? Will that throw you off? Nah, okay. All right, I didn't write anything down, Sophia, so you're gonna have to start over. What'd you say?
A student is skateboarding down a ramp that is 6 meters long and inclined at 18 degrees with respect to the horizontal.
Okay, that looks like a whole lot more than 18 degrees, but that's okay. 6 meters is the length of this ramp. Here's my student on a skateboard. All right, go ahead.
The initial speed of the skateboarder at the top of the ramp is 2.6 meters per second. Neglect
2 point what?
meters per second.
Just 2 meters per second?
2.6.
2.6 meters per second. All right, go ahead.
Neglect friction and find the speed at the bottom of the ramp.
Okay, speed at the bottom of the ramp. I can use the big 4 knowing VO and looking for V and knowing the delta X is 6, the VO is 2.6. I need to know one more thing though. I don't know the time. I don't have any way to get that. So probably what I need to find is A. What is the acceleration of the student? Because I can do that using the sum of the forces equals MA. I can do that. Okay, Freebody diagrams where you start. On the student, straight down is mg. Perpendicular to the surface is the normal force. And there's no friction, according to the problem. So those are the only forces acting on the student. The normal force is already on the y-axis. The x-axis is the plane. And so I need components of mg. Here's my y component. That's m. This green one doesn't work very well, does it? I'm going to quit using green. Did it go in? Oh, come on, Tony.
Yeah.
it did, yeah.
Do you remember that one time that you threw it and like from over there it went in?
Did it go in?
In like chemistry last year? you were
I don't
standing
remember,
over
but
there.
probably, yeah, that's great. I don't have another color now. I'm gonna have to I threw away my green, so what am I gonna use now? No, I thought of them. All right, my component here is the mgy and here's the mgx. The x is parallel to the plane, so my right angle is over here for this triangle. This angle up here is theta, which is 18 degrees in this problem. So again, make sure you have figured out how to draw components for an inclined plane. One of them is perpendicular to the surface, one of them is parallel with the surface. All right. Now, the sum of the forces equal ma, that's what I'm going to use. And either x or y, let's start out with the sum of the x forces equals ma. That's everything parallel with the ramp itself. Well, the only thing I see is mgx. Is there any other parallel force? No. So mgx is equal to ma. And mgx would be mg times the sine of 18. It's opposite the 18-degree angle, so use sine. That's equal to ma. The m's will cancel out. So you didn't have to know the mass of the student. And what you have is acceleration is equal to g sine theta. In this case, theta is 18 and g is 9.8. That's the answer for the acceleration. That's not the answer to the question, but that's the answer for the acceleration. On an inclined plane, I'm just going to tell you this. Sarah, what time does the class get out today? Oh, wait, you're not here. Anybody know what time it gets out? Is it 10:50? So we have 5 minutes. On an inclined plane, the acceleration is always going to be equal to g sine theta, if there's no friction. Because friction would add another force in there. If something's moving down an incline with no friction, this is always going to be true because of what I just showed you right here. Well, some students just learn that. If there's no friction, the acceleration is g sine theta. Okay, so whatever that is, a. Now to find the answer, what's the final velocity of whatever I got for a right there, I'm going to put right here, and then I can use v squared is equal to vo squared plus 2a delta x, and solve that for v. Okay, do you see what we're doing? Because the delta x is 6, the a is whatever that was, and the vo is 2.6. You can solve that for v. And on my paper, I got the final answer is 6.6. A, by the way, came out to be 3.03. That's what I wrote down anyway. 3.03 meters per second squared. And when you plug that in here and solve it for v, I got 6.6 meters per second for the final velocity. Started out going 2.6, at the bottom was going 6.6. That sped up. Okay. Any questions about that one now? We're going to try to do number 83 in the next 3 minutes, or maybe we won't. Let me look. 83. Oh, we do need to do 83 because I want to talk about that pulley. I'll tell you what, we're not going to do 83 right now, but I am going to tell you, I'm going to show you very quickly how to set up a problem that has a pulley with ropes hanging straight down and maybe different masses here. Okay, this mass is twice as much as that mass. So this one's gonna go down, right? And that one's gonna go up, if you let go of it, right, everybody? If you wanna know the acceleration of the system, that's going down, that's up at the same rate, because that's all one string. You can do kind of the same thing we did with, when we had a pulley here and a rope like that. The direction of motion is positive. We already know this one's going to go down, so over here down is positive, over here up is positive. The direction it moves is the positive direction. So again, set up the whole system in one equation, get all the forces on either block into that equation. That means I've got to start by drawing a good free body diagram, and the free body diagram would be mg for this thing, and the m is 2. Over here it's also mg, but the m is only 1, so not as long. But these tensions would have to be what? The same, because it's all one string. So they're going to cancel out again. Because this block's going down, so that tension's in the opposite direction from that one in terms of motion. So when I do this, these tensions are going to cancel out again, and I'll just have this and this that equals MA. So without time to actually finish that problem, I'm just kind of showing you how to set it up. It's a fire drill, but it's okay, we're in a good stopping place. I'm turning off the camera, go to the lobby, and